Gentlemen, my name is Rohit Silva. I am the chairman of IESL New South Wales chapter. IESL in the sense Institution of Engineers Sri Lanka, New South Wales chapter chair. And we're really glad, and we want to thank Professor Ambi, right? Am I correct?
It's all right.
Yeah, Professor Ambikairajah and Jackie for inviting us here and then organize this public lecture. So IESL, our chapter, normally we have public lectures and a lot of events almost in every month. So normally we used to have them in the Engineers Australia auditorium in Chatswood. So today is a special day. So we are having our lecture at the UNSW. So we warmly welcome all of you to the presentation, and we normally our presentation we live telecast via Facebook page, and then people can log into that one online, or they can watch them in the later whenever they get a free time. So before I move on to hand over to Professor Ambi, and I will do Professor Ambi will do the housekeeping stuff, because, and then I would like to introduce Professor. Professor Ambikairajah received his BSc Engineering Honours degree from the University of Sri Lanka, Cochlea campus, where I also graduated, but a couple of decades later, and received his PhD degree in signal processing, where today is going to talk about it, from Keele University in UK. He was appointed as a head of electrical and electronics and later Dean of Engineering at the Athlone Institute of Technology in the Republic of Ireland from 1982 to 1999. His key publication led his repeated appointment as a short-term invited research fellow with the British Telecom Laboratory, UK, from 10 years from 1989 to 1999. Professor Ambi is currently the head of School of Electrical and Telecommunication Engineering at University of New South Wales. His research interests include this speaker language recognition, emotion detection, and biomedical signal processing. He has authored and co-authored approximately 300 journal papers. Even I haven't read that much of newspapers. And is the recipient of many competitive research grants. He also regular review of several IEEE, IET, and other journal and conferences. For his contribution to speaker recognition research, he was a visiting scientist with the Institute of Infocom Research, Singapore in 2009 to 2018. And he is currently advisory board member of the AI Speech Lab at AI Singapore. Early in his career, Professor Ambikairajah earned the Best Paper Award for Young Members by the IEEE UK. He received the UNSW Vice Chancellor's Award for Teaching Excellence in 2004 for his innovative use of educational technology. The school awards the Teaching Excellence in 2009, in Academic Management in 2001, and again 2014, he received the UNSW Excellence in Senior Leading Award. Professor Ambikairajah was an AP-SIPA Distinguished Lecturer for the 2013-14 term. He is a Fellow and Chartered Engineer of the IET UK and Engineers Australia, and is a member of the IEEE and AP-SIPA. Ladies and gentlemen, please give a big round of applause to Professor Ambikairajah. Thank you.
Thank you, Rohita. Maybe next time I should cut down my bio, it's too long. Sorry, thank you again. Maybe before I start, I'll just give you a housekeeping. So there are 5 exits on straight ahead. If you go, there will be 2 exits. So you need to remember, in the event of a fire alarm, please keep going straight, and then you'll see 2 exits on right and left. Whichever the one you want to take, that's fine. Toilets are in this floor, as well as ground floor and up floor everywhere, also at that corner. And I don't think we will have any problem with fire or anything. We have never had it. We never had any disturbance during a presentation. So we hope keep our fingers crossed. Hopefully that there will be no disturbance. Thank you, Institute of Engineers Sri Lanka, New South Wales branch, inviting me to give this lecture. And as you know, this area is a very, very complex area to give a lecture within 40 minutes. So I'm trying to make it simpler and trying to give you the essence of cochlear modeling, so you'll have an idea of what it is and its applications. Maybe I'll give you a talk about 45 minutes, and then followed by maybe questions and answers and discussions. And then at the end, if this building was refurbished, we only moved in about a couple of months ago, 104 million university invested in this building. So if anybody's interested, I know it's very dark outside, you want to get back home, but if anybody's interested, we've got few staff around, we'll be able to show you around the laboratories. Okay, so with that, let me just start. I just need to set up something for 1 second, and then I'm ready. Just give me 1 minute. Okay, so the title is Cochlear Modeling and Future Directions. What we think is there are future directions, many directions you can go. So we are looking at one direction, and one or two directions, which I will go through that with you. Just about the university first, just one slide just to give you a feel for it. So we are the largest electrical engineering school in Australia. So there are 39 universities in Australia. There are top 8 universities. And if you take electrical engineering, we are the largest one in Australia. And then we've been ranked as the top electrical engineering school in Australia by multiple university ranking, without going through detail. And in the QS ranking in 2019, we are 36, so we are not that far away from Melbourne. Melbourne is 35, we are 36. When I started as a head of school, between Melbourne and us, there were 15 positions. We were below Melbourne, so we're now closing the gap closer to Melbourne. Melbourne is number 1 in the QS ranking in Australia. Then for research ranking, we receive 5-star. That means our research is well above world standard, or almost world standard. And the research ranking was evaluated in 2010. We got 5-star, 2012, 2015, and 18 as well. So we've been doing pretty well. Just to give you a feel for research income, we have about 25 million last year, which is a lot of money. So we've got many staff bringing in that money. The size of the school is about 2,000 students we have. When I started as a head of school, we had 900 students. So that's 10 years ago. I've been a head of school for 10 years. And we have got 2,000 students, 1,000 undergraduates, and we have got 200 PhD students. We have 46 academic staff at the moment, and our plan is maximum 50, and we will saturate at that point. We don't have expansion capacity unless we build another floor or we grab another floor. So 50 probably the maximum. And 30% of our staff have got teaching award. That means they're pretty good teachers. They're not only good researchers, they're really good teachers. I mean, teaching awards in this university come from the Vice Chancellor, plus from the faculty as well. So 30% of staff have them. And as I said to you, the university invested 104 million refurbishment, and there are many research labs, many teaching labs, looking at how we want to teach in the future, innovative way of teaching. All the facilities are available, and we've already started to do some teaching on that area. So let me just grab some water and then start my talk. So what am I going to talk about? First, I'm going to give you a little bit of introduction of human auditory system. What is it? How it operates? And then, how do we model cochlea in terms of modeling? So normally, before you build a hardware, you actually do the model, you do a lot of testing. Once you have done the testing and under various conditions, once you've done all the simulation, when you're happy, then you start to look at, how do you then build actually hardware building. So we've got hardware expert, the Shri there, a few other people. And then I'm going to look at one particular model, which is the future, not now, but we call it adaptive model. How do you adapt the model that you already have? How do you change its characteristics? That's the main part. That's the drive for us. Then little bit on cochlear implants. I'm not an expert on cochlear implants, but I'll be able to link what we are doing with implants, and particularly the behind the ear processor. That's what I will be concentrating on it. And then we can have a discussion. So let's look at speech. So speech is generated from a vocal tract, which is the transmitter, and your ear is the receiver. So human has evolved that you've got a transmitter and a receiver. You can argue they are matched. They are not matched. They could be matched filters. They could be matched. Both of them are evolved in a way that characteristics are matched. But we'll come back to that in detail. So when you speak a waveform, and when you speak on the microphone, that's, for example, a waveform. That's what I hear. And then I've learned over years how to translate into meaningful information, right? So what we are going to look at, how the human hear a sound and how that is translated to auditory centers. So just an example of a sound wave getting into the ear canal, transmitted through various pathways, cochlea, and then it ends as impulses to the neural coding. So what we are going to look at is this part. And we're going to go section by section to give a little bit of feel, and then I'll go the modeling part. The modeling part will take some time. So human auditory system, this is just physiology. You may already know this, but let's look at it in terms of engineering aspects. So if you look at the peripheral auditory system, there are three parts. Part one is the outer ear, which is your pinna and the ear canal and the eardrum. Up. Okay. Then the middle ear, then your cochlea. And the output of the cochlea goes as electrical signals to the brain. For cochlear implant people, this part, well, this basically, that one, is your processor behind the ear that you put in. And that's the one then send the signals when you do the operation. And I'll show you some example, and then sends us signals. How it does it, we'll look at it. So our part is going to be mainly here, cochlea. If you uncoil the cochlea is like a snail shape. Once uncoiled, what is it? How does it operate? And how the function, how it functions, okay? So I won't go through the detail of it. So human hearing audio frequency ranges 20 hertz to 20 kilohertz. Cats can go more than that. Bats can go more than that. Dolphin can go up to 100, 200 kilohertz. So human is about 20 kilohertz. So we're going to take one at a time. So we start with the first part, that's this part, which is the outer ear and the middle ear. So if you look at the characteristics of the outer ear and the middle ear, so let's look at the outer ear first, that part. And if you give signals and measure its response, and you'll find outer ear has got a response of kind of a bandpass filter. That's frequency. That's gain or amplitude. It's like a bandpass filter and kind of resonating around, 10 kilohertz, 3 kilohertz, 4 kilohertz, in that region. That's due to the length of your canal as well. And then if you look at the middle ear is just basically, so you got the eardrum, then there are two bones there. They translate the movement of the eardrum to cochlea. So middle ear has a characteristics, and that characteristics, if you measure the frequency response, they are the dotted one. So if you have two systems, assuming they are both linear system, if you cascade them, you get the overall system. So the overall frequency response is this one, the sum of it. So you can say that this part amplifies signals around 3 kilohertz. That's the measured characteristics of a human auditory system. That does not mean that you can only hear 3 kilohertz. You have a wider range. Different frequency position has different gain. Okay? So we move to next one. Now what we do is we look at the inner ear. Inner ear is the cochlea. So we take, I mentioned to you, the cochlea is like a snail shape, and we now uncoil the cochlea. When we uncoil the cochlea, this is the shape of the uncoiled cochlea. So I'll go back again. This is the auditory canal. This is your eardrum, and this is your two bones transmitting the movement of the eardrum into movement of the staypiece. What is inside the cochlea? If you uncoil them, the cochlea has got two partitions. Partition 1 is fluid on the top. Partition 2, different fluid on the bottom. The same fluid connected. And when this moves, this like a membrane goes out, goes inside, so it releases the pressure. So basically, those who are civil engineers would know, it's basically you're setting a hydraulic wave. Because this is fluid, this is piston moving up and down at a particular frequency, and you're setting up a wave. So what is the membrane? So there, between those two channels, there's something sitting called basilar membrane, which is a frequency sensitive membrane. Every point in the membrane is sensitive to one frequency. If you assume the basilar membrane, length of the basilar membrane is about 3.5 centimeter. That's what is coiled as a cochlea. And if you look from the top, the basilar membrane is not a straight line, it's like a trapezium. At the basal end, this is the basal end of the basilar membrane, it's 0.02 centimeter. And the apical end is 0.05 centimeter. Every point in the membrane has got a resonant property. So if you divide the membrane into small sections, measurements shows that about 8 micrometers, if you take a section of 8 micrometer, that can resonate on its own without the others. So that means 3.5 centimeter, 8 micrometer, if you divide it, you need about 4,000 sections. There are 4,000 points individually oscillating to various frequency. So think of it, you've got 0 to 20 hertz to 20 kilohertz, your frequency range. There are 4,000 points separating those. That means you can get fine resolutions, right? That's exactly what cochlea does. So what's a cochlea? Basically, it takes the incoming wave. It has got many frequencies. It analyzes each frequency and tells you, it's a spectrum analyzer, it tells you what frequencies, what amplitude is coming. That's the function of the cochlea. So a bit more, okay. Now the question is that I now just go as cochlea, basilar membrane is our important part. That's what we are going to talk. So if you look at the cochlea, snail-like, this part is the top part is the fluid. That's the bottom part fluid in there, the blue, and the basilar membrane is the one separating the fluid. You can see? This end is basal end. This end is sensitive to 20 kilohertz, and that end is sensitive to something like 200 hertz or 70 hertz. So low frequency, these positions are sensitive to low frequencies, and this part is sensitive to high frequencies, and these parts are sensitive to mid frequencies. So high to low. That's how the basilar membrane is. When you do frequency analysis, normally when you do the analysis, when you draw a spectrum analyzer, you do low to high, but think it the other way around. Okay? Because this is narrow and stiff, that's why it's high frequency. Yeah. Sorry, it's a small area. So, and imagine that this we need to model first. So cochlea has got two parts. One is we call it active cochlea, or it's called passive. We look at the passive part. So we know basilar membrane is basically a frequency sensitive membrane. Now if you look at here, I move this tapepiece at one frequency. It goes in and out at one frequency because the eardrum moves in a particular. And say that frequency belongs to a position. So if you can see that membrane bends and it gives you maximum displacement at the position where it's sensitive to that particular frequency. So if this frequency is 1 kilohertz, this will resonate. If this is 100 hertz, you will find this part will resonate. If it is 15 kilohertz, you will see that part is resonating. But you don't get one frequency, you get multiple frequencies. Speech has got 0 to 7 kilohertz comes through. So it was able to resolve all of those. And how we resolve, we'll come back. And there's an equation people, researcher called Bekesi in 1960, he did a lot of measurements. And the difficulty in doing measurements in cochlea is you can't do measurements in cochlea once in an animal, once the animal is dead, because the characteristic changes, completely changes. And you'll never get a sharp tuning. So you got to do in a live animal. And they did do some, when you do in a live animal, you can access only certain part of the cochlea. You can't access everywhere. Therefore, you can't get measurements in every place. So you get measurements in certain places, then you do some sort of interpretation or prediction. Is that so far okay? You have an idea? So we call it basilar membrane as a filter bank. What does that mean? Filter bank means it just selects one particular frequency. So what happened here, have a look at this. Low frequency coming in, and it's moving into the ear canal and moves the drum, and then moves this one, and it travels along the basilar membrane. Because it's a low frequency, 100 hertz, only activity will happen in that area. And we give a high, medium frequency, and it travels around and it sees its frequency belongs to that position. That's where activity. All the other part of the membrane is no activity. You've got 10,000 kilohertz, it belongs to that. That's part of the activity. So the activity happens in, activity means the membrane is bent. Okay, we'll show you a small demo. So what we are saying is that all these means, we say this is a filter, this is a filter, this is a filter. It could be analog filter or digital filter. We can model them as filters, basilar membrane, based on this understanding. Now I'm going to show you a simple example of a simulation that people have done. It would be good to have that simulation to get a view before I go into modeling. Okay, now go back. Now, Ming's told me something I have to do to go back. Okay. It's about 1 minute or 1.5 minutes. This is the cochlea modeled, and they show you, sorry, it's just a simulation. Or animation. Uncoiled cochlea, cochlea is uncoiled. That's the membrane. Going to be excited by one frequency first. Low frequency, mid frequency, high frequency. All three together. Music. That's what you'll hear. You've got activity everywhere. That animation shows how the membrane bends itself for various frequencies. Okay? Okay, let's move on to the next. Okay, models of the cochlea. So let's look at one model first and then we take it further. Now those who have done electrical engineers and also mechanical can have a look at this one. So what we're going to do, we take the basilar membrane, we're going to make them into many, many sections. There's a section 1, section 2, we can make many sections, right? And one section of the membrane is vibrating. So what is it equivalent to in mechanical engineering term? It has got a mass, so it's a mass there. Vibration must have a spring action and should have a damper. If you've got mass, spring and damper, you have a resonance system. I'm sure all the mechanical engineers would have known that. If you translate into electrical, they'll say, oh, mass is equivalent to an inductance, and damper is equivalent to a resistance, and a spring action as a compliance is equivalent to a capacitor. So you got a mechanical engineer this side getting understanding in mechanical way, electrical looking at as resonance. Like you'll know if L and C has got a particular value and it will resonate at one particular frequency. And remember, so what we're going to do is that we're going to put many sections of them and cascade them into a mechanical system or electrical system. But when you have a membrane is not on its own. There's fluid on the top. So fluid is mass, so which is equivalent to an inductor. So the circuit should have an inductor as well. That is the fluid mass. So for this section of delta X, you've got a resistor, inductor, and a capacitor, and a fluid. And we get two voltages. One is here, one is here. This is the input voltage. Now what I'm going to do is I'm going to take the next section, the yellow section. So what happened is I connect the next section here. So it's becoming now a cochlea section 1 followed by a section 2. This is mechanical engineers one after another. Then connect the next one. I got the third, many sections. That's the end section. So the cochlea is now modeled as a resistor, capacitor, inductor. How do you get the values? Well, that's a separate research. And there are measured values available. We use the value. But then being clever electrical engineers, they do other things, you know. Or mechanical engineers, same thing. Now, when you come to the end, when you look at the cochlea earlier, you would have seen the picture. At the end, I may go back and just to show you the end. Sorry. A diagram I want to show you. You see, at the end of the cochlea is the membrane does not go up to the end. It goes up to the end, and there is a fluid balances its pressure. So there's a fluid mass at the end. That's called helicotroma. That area is called helicotroma. So what happened is that we need to terminate them with the mass of the fluid. So you've got a complete transmission line. Now you analyze this to model them. How do you analyze this transmission line? Right, loop equation. So true electrical engineer will go for a loop equation, and you can use nowadays. You can use the computer to solve it, right? Or you could do it other way. You could think in terms of filters. So what we have done is we have done calculation on these ones. If you were to look at this particular section, we look from this end and see what this end look like. So we put the loading effect back onto this, and we have a model which will give us, when we do the modeling, we give at any time we'll get a low pass filter, a resonant filter, and a resonance zero. So a section can be modeled, even though they are cascaded, can be modeled by 2 filters or 3 filters. Filters are basically resonant filters and non-resonant filters. And you can see one of them giving you a peak, one of them takes away the energy, one of them shaping the whole characteristics. So we can actually prove that. We don't need to go through detail. There are papers we have published. So a transmission line model can be squashed into a single model, which can be represented. And we have ways of selecting all these values to represent each point in the cochlea. Okay? So now I'm going to show you, I'm going to say, okay, I have got a low pass filter, a digital filter. Now I want to implement everything digitally. So I translate them into digital, and I've got a resonant pole, I've got a resonance 0. So that's one section, that's section 1. I take the output from here for each section, membrane movement, then section 2, and so on, so on. So I got many filters. So you can design this one with 128 sections, 4,000 sections, depends on what computing power you have. And each section consists of that sort of filtering. Okay? Before we go any further, those who have done electrical engineering will know that, where is it? You would know this. If you take this, if you modify these values, you will get different characteristics. This is called bandwidth. By selecting that, you can change its characteristics. That's what we are doing for active cochlea. That's what the cochlea does, actually. It changes its characteristics. I'll show you that in a minute. I hope it's not too heavy for you, but you'll see. I'm trying to keep as simple as possible. Here is an example of a membrane. Membrane means cochlea has now been modeled as a filter, filter 2, many filters. I have middle ear here. I give a sinusoidal input. And then I know this has a frequency. This is my membrane distance, this direction. That's my membrane. That one is my membrane. And you can see I can, in model, it gives my peak at that point. And when I measure that point, that's exactly same frequency what I give there. So my model is right by doing that. But remember, when your eardrum vibrates, and when the stapes vibrate, there's pressure there. So heavy pressure. But then the pressure should decrease at the point of resonance. So you can see pressure waveform at the start. This is the basal end, very high pressure. It decays it and goes to 0, and it does not travel because this waveform can't travel any further because that point is resonating for that frequency, mean all the energy is taken out. Nothing is left to travel. So that's the modeling. That's how we model first, right? And also we want to look at its measured characteristics. So we match this filter characteristic with the, we calculate its characteristic and measure them, match them with the measured characteristics as well. Okay? We have to do all of these in order to get actual cochlear design. Now, we are in the next part. So we have now modeled the basilar membrane. So basilar membrane is just a membrane sitting here. Signal comes in, every point is moving up and down. That movement has to be picked up by something because that movement has to be sent to the brain. So in the cochlea, on the basilar membrane, there's something sitting that what we call is this part, tectorial organ of Corti. So I took a cross-section. I took a cross-section of a membrane, just one section. That's your membrane, you see. And on top of the membrane, these fellows are sitting. So if you have got 4,000 points, 4,000 of them are sitting. There are 30,000 hair cells. The function of them are, they take this movement and transmit that movement to the brain. How do they do that? If you think this moves upwards, there's liquid around here, they fall through this, and they bend this hair cell. That's a hair. These are the hair cells which send signals to the brain, and these are the hair cells receive signals from the brain. So the way cochlea works is that you can say here in a block diagram, that's the outer ear, middle ear. This is your basilar membrane modeled using filters, right? Same thing. And then basilar membrane movement is passed through inner hair cell, through that hair cell to the auditory processing. And then the auditory processing sends some control signal to the membrane to change the membrane characteristics. If you don't have this pathway, then we call it passive cochlea. It's all in one direction. Whatever membrane does is what it receives. If you have this pathway, we call is a feedback loop is closed, then we have got active cochlea, and I'll come back to that in a minute. Okay. So just to show you another modeling, and you will see here is I picked up one hair cell. If the hair cell is, think of this way, hair, the cells are here, and it has got hairs like this. When the membrane moves, the fluid bends these hairs. Bending a hair in one direction is similar to half-wave rectification in electrical term. So to model, you put a half-wave rectifier. Then think of it, bends it, then it's come back straight, because the membrane has to come down, then bends and come back, which is equal to charging a capacitor, discharging a capacitor. So we can model with the resistor and a capacitor as a hair cell model, right? So the output of the hair cell models are the one that being sent to the brain. So here now I'm going to show you a couple of models now. Here is the model that we just discussed about it, and you've got filters of basilar membrane, and you've got hair cell picking up all the membrane movement and sending us electrical signal. If you look at the characteristics of any of these filters, I mean, I've drawn few of them, they will look like this, you know, any of these colors. And they've got a specific cutoff and specific shape. This is a similar model to this one. That's similar to this. This is the exact. Assume this is the exact. But this is approximate. It looks similar. If you look at, cut it off there, it looks roughly same. See that? But this is the model that you'd have in the implant behind the ear. Is this one, not this one. Too complicated to do this one before. Now with the technology, with all sort of you know, fabrication facilities, and you know, this can be implemented. So that's why we are now started again to look at this one, so that behind the ear process could have different characteristics. It can do so many other things. We'll come back to that. So this is what you will find if you take a behind the ear of a cochlear implant. They have a microphone here, plus a processor is that parallel filter bank. That's all they have. What we really need is this one, and we'll come back. Because this sharp character is very important to remove noise and things like that. Here it can't remove that sort of shallow. Here's an example, same thing you've seen it. In our model, we gave 3 sine wave at this point. We looked at the membrane, how it behaves. Then we put the inner hair cell through it, and we see the output comes there. So we know this is how we verify our model. Then we give a speech waveform. This is a speech waveform. The waveform says 3, a word 3. TH is a very low energy one, 3. So it's a low energy region, and this is a high energy region. And you can see that, you know, for this one's a lot of high frequency in it. Therefore, membrane has high frequency this end. You have a lot of activity on the membrane. This has got a lot of low frequency region, so low frequency energy, so membrane has activity in the low frequency. So this is just an example to show how we actually test the model, just to get a feel for it, okay? Now, we now move into the next level. So I've shown you taking a basilar membrane and modeling them into small section as filters, then looking at the filter output using another hair cell model to pick up signals. Okay, once you have done the transmission line model. But Cochlea does amazing things. Okay, what's the range of the input signal that you can have without any pain? So the range is from 0 dB sound pressure level to 120 dB. 30 dB is somewhere is the normal conversation. So if I don't have a microphone, if I have one-to-one conversation, what you receive is around 30 dB, which is a comfortable one. If you do have some sort of a problem with the ear, then you need slightly more volume. 40 dB is another comfortable one. But if you keep increasing, 120 is threshold of pain. When you reach 120 dB, you're not going to listen to plane taking over all the time. Is rich or rock music, very heavy music, 120 dB, and eventually, if you go back to the cochlea, the basal end is high frequency, they will be damaged. So your frequency response, if you look at when you are young, that's your frequency, that's your amplitude. If you say overall frequency response was pretty good, that's low frequency, that's high frequency. Your frequency response is something like that, say. As you get older and older, because you are damaging the basal end, this will be decaying, your band comes narrower. So as you get older and older, you need to increase the volume if you really want to hear music. And so that's a separate thing. So the thing is this way. If you have 0 to 120 dB, how does the cochlea code that? How does that transmit to brain? You can't transmit 0 to 120 dB to the brain, no. So it must compress that. So 120 dB is a big range, and that goes through, and there is compression technique. So many places there's nonlinearity. So in the middle ear there's nonlinearity. So the two bones I showed you, for a small sound it'll hit like this, like a hammer and an anvil. When the sound gets really very heavy, it just rotates. That's the saturation. That's the hair cell. It can only bend so much. So that's also a saturation point. All these combined, you can then see as 0 dB increases amplitude, 120 dB decrease in amplitude. That's how it does the coding. So that's the beauty of the cochlea. It can just compress the range. And how do you do it? And how do you incorporate that into in a cochlear implant behind the ear? It's not easy. If you use the parallel filter bank, your compression is only a certain amount you can do. You can't do full compression. If you want the full compression, you need this cascaded filtering. So that's the next generation system. People could still argue, no, we will be able to do this. They can reach, this is where you want to reach, but you could do this, or you could do this, or you could still all good enough. But to reach maximum, you need to have complex system. So we then developed a new idea looking at artificial intelligence and how we build artificial intelligence into cochlea. So we applied for a grant to the Australian Research Council, and we received a grant for adaptive models of the cochlea. So that's what we are working on it, with the view to provide a future behind the ear process of a cochlear implant is it will be a useful one. That's what we are working towards. We haven't done the research yet. We are still working towards on that. So let me explain what does that mean. Now we come into, so far I explained the modeling and passive cochlea. Now we come into active mechanism. What is an active mechanism? Have a look at this. If you look at this diagram, you see the red line is a small, the membrane is only giving a small deflection. So let's look at this way. You are giving a talk, suddenly something dropped. It's a very small, low level signal, and you are able to pick it up. So the system should have to have something. So as soon as it detects there's something, it increases the outer, there's a feedback coming from here saying that I can't hear. Within a short minute, there's a force exerted in the basilar membrane. It produces a gain. So it gives you extra gain to pick up that signal. So that gain increase needs to be included in the model. How do you do it? It's a part. Human can do it, but for future modeling, we need to have that. That's we call it active gain. That's what our research is at the moment. Currently, we are working on it. Not only that, we also need to look at it that normal cochlea would have, this is its characteristics, like its passive mode. But as soon as you have a active mode comes into play, it needs to provide a gain. Because the membrane has to change its characteristics to provide the gain. How do you model that? Because you have to model and then eventually hardware. So how do you model that part is also another part of our research. And not only that, these are measured characteristics of the cochlea. How do you map this one? That means if you look at it, when you give the higher input signal eardrum, you see previously you had a very good selectivity, now it's become rounding. So the center frequency is shifting. So you need to provide that characteristics as well. All these need to be introduced into cochlear modeling. You could ask why we didn't do this before. Going back, 30, 40 years ago, we didn't have the facility to do it. We didn't have the computing power. We didn't have the understanding of everything. Now modeling techniques have improved. Computing power is there. People are able to do fabrication with this very tiny, small chip can come into play. And if you were to fabricate this one, people can do that. And low power. If you have got, currently Cochlea has got only 22 filters. We are talking about 128 filters. The amount of power required to implement that in hardware. So all those need to be looked at. So I'm just going to show you how do you do active. No, not my equation, but just give you a feel. Remember I showed you, this is our future work, current work. Showed you this, I took a section, this is the top part of the fluid section, this is the bottom part, that's your basilar membrane. Now the understanding is how the feedback mechanism work is that this tectorial membrane actually oscillates at a frequency. And there is hair cell there, they also combine oscillates. So we need to remodel it. So earlier model only had basilar membrane only, that's all you had. Now you need to have tectorial membrane has to come into play, plus this connection between those two has to come into play. If you translate that, this is your electrical equation for one section. It becomes complex. And because there's a feedback, the characteristics change. This is the feedback mechanism. You will have to have additional current in the system, voltage. So if you redo this one, so you can see now when this vibrate, this pull this one also move upwards and downwards. Previously also it happened, but we did not model that. Now we are going to model that one. So that's what it looked like. Earlier it was a very simple one. Earlier you only had that part for modeling. Now this is the feedback mechanism, plus this need to come into play. You've got all sort of problem now. You need to make sure this resonance frequency, this should be same, or the characteristic showed there's a shift. So you can do the shift with this. So this need to be modeled now. That's the current work. How can you model this cleverly? Not writing equation, no. We'll be sitting there for days and days. And so that's what we call active cochlear model. Recently we did some modeling, some work. We provided we took the inner hair cell output, we provided some feedback, and we modified the characteristics, and we were able to demonstrate something. You can see here, do you see the blue line, which is the passive cochlea? So input signal comes in, the blue line is there. Sorry, discard. Oh, okay. We have all sort of technology here, and some time they're ahead of you. So if you look at the blue line, that's the passive. So there were two signals. One is high amplitude, is maintained. Other one is low amplitude. You see that? With this adaptive mechanism, similar to what active cochlea does, you see it gives you a gain of that much. Active cochlea boosts the signal up. Cleverly you have to boost. You can't just simply say I'm going to boost the signal. No, it's a complex system. So we have done some work. Some of the PhD students here, they know, they are working on this one. So ideally, models of the cochlea should exhibit level dependence. Depending on the level, it should vary. It should provide sharp tuning curves. And if it gives you gain, then when the signal is gone, it should come back quickly to the normal state. Very fast adaptation. All these need to be included in the cochlear feature models. And this is another example. If you do a spectrogram, those people know, this is showing you this is frequency, showing you for the passive cochlea, where you can see the active cochlea picks up lots of frequencies which were not there before, and which will be very valuable, very useful for cochlear implant users, additional information there. So the additional information, maybe I just give you one example for you. This information is high frequency information. And this information is something like, if you are talking to somebody on the phone, if I talk to somebody one-to-one, the bandwidth is 7 kilohertz, or I say it's B or V, without even looking at me, they're able to say, you said B and a V. In a telephone environment, the bandwidth is only about 4 kilohertz. This information is not there. So if you say a B and a V on a telephone, most of the time you'll ask, did you say B or did you say V or did you say V or V? And there are fricatives, which are high frequency content, and are very hard to detect on a telephone, right? So, there will be signals, but the gain is not enough for you. So it will be even difficult for a cochlear implant user unless you have got some sort of gain controller like this. So that's all the modeling is. I've shown you what has been done on a passive, it was very hard to put this presentation because there's technical there, non-technical there, but we don't want to give all block schematic. So a little bit on cochlear implants and what people do, and just to get a feel, and then what we are doing future, just one block diagram. So cochlear implant system would have, you would know, everybody know those who are here, and they are experts than me, they are the users, so they know better than me. And so you have this sound processor, they call it a sound processor. You have a microphone here, and this is what we call behind the ear processor. That's your filters. And the output from the filters are sent here. You have an RF coil here. Then you do an operation inside, you have a receiver. And then this is being fed into the cochlea. There are 21 electrodes altogether because there are 21 filters. There are 21 filters, 21 goes out and 21 fed in. So you can see these are this is cochlea sliced because it's a snail shape, it's sliced, and the doctors do the operation and push the thing inside. These slides, I got them from Cochlea Limited, so it's not my own slides. And you will see that these can go only up to certain distance. You can't keep going all the way through. No, you will damage sometime. So the electrodes are only going up to a certain level, and you can see this is a MRI scan of the electrodes, how they look inside. So very simply, that for implant users, you've got a microphone, a sound processor, and then a cable going in with something here is in a kind of a round shape here, transmitter coil, and it's transmitting all these signal coming from these filters into here, and that's been then directed to each electrode goes inside the liquid. You know that cochlea has got liquid on the top, bottom, and then basilar membrane. Inside the liquid it goes, and then current is generated, and that excites the cells. So this is how it looks like. They have a microphone, front end, filter banks. The filters are this. This is the filter characteristics. Very simple filters, 22 filters. And electrode signals, if you plot them, they look like this. If you have more electrode, more than 21 electrodes, if you've got more of these, then you will see many dots other places as well. Right? This is the signal the implant users receive, and from that you need training, speech therapy, eventually you'll be able to recognize sound. Now, if you, I will show you later a slide, just slide one. So we are now trying to replace this one with some mechanism where we will change the characteristic, we'll have a gain control, we'll have a compression. So that's what we want to do. Maybe they are cascaded. Maybe we come back, another student working on parallel model, exactly same model we can provide. We may not be able to provide the compression, but all the other things. So we work in both models. So what's the future trend? What are we planning to do? Integration of auditory model with deep neural network or machine learning. We want to have machine learning. So once we have developed this behind the ear processor with machine learning, it should be able to learn the characteristics of a person as well as environment and automatically adjust everything for the person. You don't need to make changes. So what we think is that these are our filters that we are going to call as tunable filters. They are not fixed filters. Their characteristics will change. There will be a DNN-based controller controlling this. Then there will be a feedback-based controller controlling this as well. Same as what I explained, the hair cells. And then we want to use the same front end for speech recognition as well. So we'll have another DNN built in. So you may ask me how you're going to do it. Maybe in a year's time I can tell you how we probably would do it. Now we are investigating what's the best possible of incorporating this into this model. Sorry, I'm kind of... so that's what we are currently working on. This is our funding is for. Our funding is to develop this one. And this can end up as a feature processor. So if you take, for example, current cochlear implant, parallel filter bank, and a human, we'll take a sound called R. So for a normal person, an R would have 1 resonant, 2 resonant, 3 resonant, very clear, because you've got so many cells. There are 30,000 cells picking up all the movement. You'll be able to detect this one. This belongs to R. This is amplitude, this is frequency. There's one frequency, there's another frequency, another frequency. Those are the 3 frequencies transmitted. For cochlear implant users, you only have 21 electrode. For some reason, if the sound is, if these 2 frequencies are closer, they don't have enough filters to separate them. Therefore, this will look like that. Instead of 3 peaks, they may see 2 peaks. By learning, they will be able to figure out what the 2 peaks, therefore this should be the sound, and there's a certain learning. But if you can provide, more information, maybe with a gain controller, able to provide a new processor. Now, if you have cochlear limited guys here who would say, these are all wrong, we have a different way of doing it. Certainly. Nothing is, as I said to you, human is here, this is the human cochlea, here is our basic system, every time is improving. There's nothing between here is, this is right, this is right, this is right. We are trying to reach, can we do near enough to human? What's the clever way of doing it? And you may come up with a different filter in the future. Different filtering technique completely, not the way we are doing it. But we are just modeling what Cochlea does at the moment. So feature models of the cochlea will include active feedback mechanism, improve the detection of the signal. Filters in the cochlea would have adaptive feedback, and then it could lead benefits to cochlear implant. We don't know, we haven't tested it, but we feel based on the characteristic. So future implant people will be able to benefit out of it. That was what we think. And that's generally the work that we are doing. It is more complex than what I have presented. I just want to let you know, I was trying to keep it simpler. And when you get into it, and it's just, because you could ask me why? Because in order to do all this modeling, you need to have actual measurements done in the real cochlea. But accessing the cochlea is not possible in every place. So people have done one measurement on the high frequency, one in the mid, one on the low, roughly. That's all you have. You can't just access every place. Okay, the last slide just about me, not boasting, but just to give you back, and there are Sri Lankan graduates here. I'm originally from Sri Lanka as engineers, Institute of Engineers, Sri Lanka. So just to give you, first one graduated in 1974, so very old man, but I'm still energetic, okay? So you can see 1974, here's my colleague here sitting there, Chula used to teach me how to analyze the circuit, Thank you, Chula, all your help. And then we both worked in Ceylon Institute of Scientific Industrial Research, which is the only research institution like CSRO here in Sri Lanka. Then I was the first person to be awarded scholarship to go to Phillips International Institute. They never had anybody from Sri Lanka. I was the first one. I had to go and set up the standard. I invented with them, co-invented the radio tuning. So the automatic radio tuning in your car, you press the button, it finds the station. You got to give me some credit for that, okay? I was part of that. But I don't get any money. We were students. We were students. Did my doctorate in 1982 at Keele University. Then I was a postdoctoral fellow, just to show you the academic careers. Then I was in Ireland as a head of department, and I was a dean of engineering of a major institution. Then during the time I was in British Telecom Research Lab. They normally invite people as a visiting fellow only twice. I was invited 10 times. So that tells you, we are doing something good. Then 2000 to 2008, I was here deputy head of school. Now I'm the longest serving head of school in electrical engineering in the university. It's 10 years now. I've got many awards. I don't want to go through that. But I want to tell you something, the last line. All these successes are the outcome of our foundational education. It was provided by Sri Lankan University for us. The best education. If you ask me what we got from Sri Lanka, is the education. And there's one more thing you get from Sri Lanka. Anybody can tell me if you can think of it.
Long names?
No, long names there. I got a student for 26 letters she has. Okay, so in Sri Lanka, it's only Sri Lankans can answer. So it's a very good education, high school as well as the university, fantastic, a deeper knowledge that helps you to do all sort of leadership work. But not only that, Sri Lanka also provided all of us, and I hope this is also free education. We never paid a penny to study there. That's the beauty. You're paying a lot of money to study here. We never paid. So, it's a country where people have, have good education. And I'm not saying there are many people, many engineers here from Sri Lanka, many students who are future leaders. I am one of them. Studied long ago, and me and my colleague here, Chulathunga, we all are doing well. Thank you.
VC might hear you.
What's that?
The VC might hear you about re-education, so tune it down.
No, I think they have to think about it. Okay, thank you so much. Thanks for coming. And now, the last part is if anybody's interested. I know you have to go home. If you want to see the laboratories or selection of laboratories, we've got a few people we can show you around. Sorry.